This is now the second part of our report, which is robotic biomedics of intelligent mobility communication. Flying, mobility and mobility. Flying, walking, crawling, and moving. If you're wondering what is motility or what is the difference between motility and mobility, motility demands movement. Mobility is the possibility of a thing or a living organism to be moved. So mobility. Motility, for example, if I move my hand here, it demands movement, diba? So if I move my hand, and actually it depends. Because not all living organisms have motility. Like plants, they don't have motility, but we humans have high motility. Technology must have the ability to move for it to have interaction with its environment. Mechanically affected, controlled motion is a distinguishing aspect of robotics. So it means that it is made mechanically and it is controlled by an outside force. Motion can be either motive or locomotive, as I have mentioned earlier. Significant challenges of imitating living organisms. Most available motors do not behave like animal muscles, neither mechanically nor in their control. Of course, if scientists either imitate the living organism as just its physical appearance, but inside the muscles in a living organism does not work just like the mechanically made imitation of the living organism. Today's robot technology cannot maintain or repair itself. So we need to have more robust materials or sturdier materials for it to have a longer lifespan. Various applications require varying motive requirements. For example, a robot on Earth maybe fine gallivanting on the surface, but when you put it on Mars, the terrain there on Mars is not the same as the terrain on Earth. So it might be faulty, or it may have complications. That means varying motive. Locomotion principles. Robots presently display a wide variety of locomotion. Scientists have imitated insects or other animals like this one, which is a leg sprawled hexapod, meaning it has 6 legs. Leg sprawled meaning, I can't explain it, but it looks like this naka-scroll siya. Tapos, this one, the leg sprawled hexapod, it has 6 legs because it is a hexapod. And it was based on pH because cockroaches have strong legs, fast, and have high locomotive ability. Most current-legged robots do not employ mechanical compliance, meaning they do not comply like the ones in the living organism. Mechanical compliance means complying with the processes to be able to gain the desired output. More than 20 years ago, Mark Riper developed springy, dynamically stable Lego robots. So that is a picture of Mark Private's robot. The viscous properties of compliant material inlet biomaterial also dampens the vibrations associated with the. So the viscous material absorbs the shock, which is the preflex. Please remember that. This is an example of what I said earlier about the Lex Dual hexapod. This is Stanford's design of Sprolita robots. Sprolita is based on the common cockroach, which I said earlier, and uses a unique method of locomotion in which the 6 legs of the motor has 2 alternating angles. The Sprolita can move at several meters per second and walk over obstacles without any type of sensors or complex algorithm. Next. The iSprawl, a family of the Sprolitas, shows the same bouncing stable locomotion patterns in as those seen in images. The latest robot in the Sprawl series, the small 0.3 kilograms autonomous iSprawl, runs at 15 body lengths per second. It's fast because not as fast as the cockroach, because the cockroach runs at 50 body lengths per second. But it's fast enough because it's 50 body lengths. The mini WEGs, or PROF, Case Western Reserve University, is smaller and lighter than iSprawl. It predates iSprawl and runs at 10 body lengths per second. It's slower than iSprawl. Mini WEGs also runs rapidly over obstacles that are taller than the WEGs. Like for this instance, it can jump, or this one, it can climb. This one has adhesive legs, so it can crawl the walls. The Rex robot of McGill. This is a picture of the Rex robot. Next. Rex robot is a 6-legged robot with inherently high mobility. Climbs in rock fields, mud, sand, vegetation, railroad tracks, telephone poles, and upslopes and stairways. It has a sealed body making it fully operational in wet weather, muddy, and swampy conditions. I have a video to show of the Rex. As you can see, it can walk, it can crawl perfectly fine on those rocks, obstacles that are not taller than it. But that's this is just the details of why it was based on cockroaches. The legs of the cockroach have different functions. The 2 front legs serve as brakes. The 2 legs in the middle move back and forth. Either speed up the cockroach or slow it down. To the rear, move the roach forward and can move about 50 body lengths per second, as it said earlier. When a roach runs this quickly, it sometimes races up and runs on its back legs only. The force of the air it encounters keeps it upright. Flexibility, hybrids, and reconfiguration. Real-world performance can require flexibility and multi-purpose applicability in mechanical automation. This is the snake robot S5, which just looks like a snake robot that I supposed The snake robot S5, built by Kevin Miller, demonstrates untethered legless snake-like slithering locomotion. Miller's S1 to S5 built on earlier work by Shigeo Hirose of Japan, in which oscillatory deflection sharpened down the length of the snake, causing the snake to move forward while offset to the oscillation state device. Meaning what you saw earlier in the snake, okay, there are contractions, the small contractions, it moves, and oscillating meaning pag ganon, oscillating